The following program is brought to you by Caltech.
Good evening. I am Ravi Chandran, and I am the Director of the Graduate Aerospace Laboratories in the Division of Engineering and Applied Science. I would like to welcome you to tonight's Watson lecture. Before I introduce our speaker, I want to mention the next Watson lecture, which will be on May 19th, and it will be given by Professor Thanos Siapas of the Division of Biology, and he'll be talking on neuronal mechanisms of memory formation. It gives me great pleasure to introduce our speaker today for the Richard C. Bierderbach Memorial Lecture, Dr. Chiara D'Arroio, Assistant Professor of Aeronautics and Applied Physics. Dr. D'Arroio was born in Ancona, Italy. She received her bachelor's and master's degrees in mechanical engineering, magna cum laude, from the Politecnico della Marche in Ancona, Italy. She then went on to the University of California, San Diego, where she received her master's and PhD in material science and engineering. She joined the faculty at Caltech in 2006. Dr. D'Arroio's research is focused on acoustic metamaterials and their engineering applications. She has made a number of pioneering contributions to this field, and she will share some of them with us today. Her research is multidisciplinary and is at the interface of material science, condensed matter physics, and solid mechanics. Her work has been recognized through numerous awards and honors, which include a Career Award from the National Science Foundation and a Young Investigator Award from the Office of Naval Research. She has also received the Richard von Mises Prize from the International Association of Applied Mathematics and Mechanics, and she was also named to the Future World Leaders Initiative at the Science and Technology in Society Forum in Kyoto, Japan. Ladies and gentlemen, please join me in welcoming tonight's speaker, Dr. Chiara D'Arroio.
Hi, thanks, Ravi, and thanks, everyone, for coming to listen to my lecture today. It's a pleasure to be here and be able to address the audience of a Watson lecture at Caltech. So today, I'm going to be speaking about the development of new materials starting from the dancing beats of the Newton's Cradle. I'm going to try to play the movie here. This movie has been shot by some of my grad students and postdocs in the lab at Caltech. And it's supposed to actually, and I brought, by the way, the toy here with me in case we can run some live experiments later. It's supposed to show what a Newton's Cradle is. So this is the toy that entertains bored executives and mesmerizes children with the promise of a perpetual motion. Now, if you look carefully at this and stare carefully at the motion of these beads, first of all, they're by far not running in perpetual motion, but also they cannot defeat the expectations of a perfect dance in which the expectation of the first particle is to hit the others, the middle particles would stay still, and the last one would fly off. So let's look at the fundamental idealized motion of a Newton's cradle and understand the common misconception behind it. So the Newton's cradle has been taught in many physics textbooks and lectures for explaining the simple momentum conservation and energy between one particle and the other. So what the cartoon here shows is actually the motion of the first particle impacting a second one and coming at rest. And in the absence of friction or losses, dissipative losses, for example, viscous drag, this could be continue on and on forever. Now, let me show this in a cartoon on the left. So if we consider the momentum conservation, we assume that all the beads are actually the same and they have the same mass. The first particle is lifted up, assumes an initial velocity v0, v01, and it's going to start impacting the others. And once it impacts the others, it comes to rest. And the second particle would now assume the velocity v01 while transferring the momentum from particle to particle. This, at least, was the expected concept for a Newton's cradle dance. Now, if you actually remember looking carefully at the previous and so on and so forth until the actual last particle would fly off. Now, if you remember the movie that was played earlier, you see that that was absolutely not the case for an experimental setup. And so what we can do is that I can actually play the same experiment here on stage. I don't know if I can get, yeah, there you go. So you'll see that it was a realistic experiment run in the lab. So if you look carefully, you'll see two fundamental things. The first one is that the central particles actually keep swinging. The second one is that there are gaps opening between the middle particles. And at the end, the particles are going to come at rest and not continue swinging. So at this point, the board executives that would be in the room might start thinking that, yeah, we bought the cheap one, and therefore we should have invested more in these experiments. While the scientists in the room might think that there might be something missing in the physics of this explanation. Finally, the engineers that might be in the room might just observe the phenomenon and think, well, what can we do with it? So I'm going to start for the next. In the next slide, I'm going to take the assumption of a scientist and assume that this motion actually is not correct. So if we look at the physics behind it and analyze what really happens in a Newton's cradle, it's easier to start from a larger number of particles. What you'll see in this case that if I impact the first particle in the chain, what happens is that a solitary wave forms right after the impact. So in this case, the momentum and the energy, it's not transferred like was mentioned before from particle to particle, but rather from the first particle to a series of particles adjacent to the first one. So the solitary wave that forms, it's actually a nonlinear phenomenon that's related to the geometry of these systems, and I'll explain that in more detail later. So once the solitary wave forms after the impact, it travels through the chain at a constant speed and maintains its shape and amplitude unperturbed. It is important to mention that the actual solitary wave size is always 5 particles, and we'll come back to these along this talk. So at this point, I'd like to introduce one of my graduate students. This is Nicholas, and he's a third-year graduate student in aeronautics here at Caltech. And he has recorded an experiment for us to show actually the 5 particles width of a solitary wave. So I'm going to play the movie now.
This experiment is designed to illustrate, in practice, the 5-particle width of the solitary wave. So let's imagine we have a Newton's cradle, but this time we're going to make it longer. What we can imagine will happen here is if we disturb the chain in a way similar to previous experiments, this time by taking a ball and rolling it down the ramp so that it strikes the chain, we will generate a 5-particle wide solitary wave that will travel down the length of the chain. The fact that it is a 5-particle wide single pulse is important here. This means that all the energy, all the information from the impact by the striker is stored in only 5 particles. So what you should see is the striker hits the side of the chain and then several particles fly off the other end. Not one, which is a common misconception from the Newton's cradle toy.
So anyway, as you can see from this experiment, the impact of a single particle on a longer chain of beads distributes the velocity among several particles. And this is why the Newton's cradle toy actually doesn't work. This is also why one can never buy a Newton's cradle toy composed of more than 5 or 6 particles. Because evidently, the larger number of particles, the more it would be evident that the assumptions of perpetual motion wouldn't work. Now, this has been studied extensively in the literature, and in case some of you might be interested in constructing their own Newton's cradle, I suggest reading this paper in the Proceedings of the National Academy of Science, which actually studied the number of beads that would fly off as a function of the amplitude of the swinging of the beads and the number of particles. So, but the fundamental question is, what type of information is carried by these solitary waves in a chain of particles? And the answer to this is that the mechanical swinging of a particle over a chain of spheres excites a compressive pulse or a longitudinal wave, also defined as an acoustic wave. So on the right-hand side of the screen here, there's a definition of acoustic waves as longitudinal waves in which the oscillations of the medium and the particles are actually in the same direction of the motion of the wave. What you see on the left-hand side instead is a picture from the 1960s in which sound waves were visualized by means of a very clever experiment. So the gentleman on the left is holding an acoustic device or an acoustic lens capable of focusing sound waves in air. And the horn that you see at the very left is actually emitting sound waves that travel through this space, cross the acoustic lens, and propagate through it. So the interesting part was, I guess, the clever experiment that at Bell Labs was run was able to utilize a microphone connected to a light bulb. Now the microphone was scanned in the area adjacent to the acoustic lens, so that the intensity of the microphone, or the sound picked up by the microphone, would power up a light bulb, and it was possible to actually construct a superposition of images to see colored bright and dark fringes for imaging the actual propagation of the longitudinal waves. So this shows that, okay, sound waves or acoustic waves can travel in air and corresponds by a series of peaks and valleys of compression and tension. Basically, the particles in air move with respect to each other and transport the information, the sound information. But acoustic waves are not limited to air, for example, or other fluid media. Acoustic waves can travel also in elastic media. So this slide here represents a series of waves, or what type of waves can travel in an elastic medium. In this case, this is a slinky. So if I play the movie, you'll see that the animation shows two types of wave. One is a transverse wave, and the other one is a longitudinal wave. So for the acoustic waves, we're going to focus on this case, in which you'll see that the particle, in this case, it's one spire of this slinky, moves back and forth from its equilibrium position, while the wave travels along the horizontal direction. While in a transverse wave, which is typical, for example, of waves in the ocean, the motion of the particle goes up and down, while the wave tends to propagate in this direction. So one of the first questions is, now that we have realized that acoustic waves are everywhere to be found and not only allow us to hear and communicate, but also are present in different other systems, I would like to focus on three fundamental applications for acoustic waves that are used in common everyday life. So the first applications I'm going to be focusing on is to look at how we try to control elastic waves and, in general, vibration and noise that are emitted, for example, by mechanical motors or in aeronautical and aerospace application by utilizing, for example, acoustic absorbers or vibration absorbers media. Another application in which acoustic waves or acoustic systems are used to control the wave propagation are biomedical systems. One example here is actually picturing an ultrasonic image of, in this particular case, it's an ultrasonic image of my son, Ari, that was taken about 6 months ago. He is now in the room somewhere in the back, and he's 6 weeks old attending this lecture. But however, ultrasonic imaging is used often to image the interior of the human body by emitting sound waves that can travel and reflect from the internal portion, from internal parts of the body, and then are acquired by transducer devices. The last application that I'm going to be focusing on today is the use of acoustic waves to evaluate materials, or to evaluate the structural integrity of materials. In this particular case, it's called non-destructive evaluation or structural health monitoring of systems. So what you see here is that you can use, for example, high-frequency acoustic waves to send them through, say, an airplane wing or other structural components like a bridge, and determine if the material has been fatigued or cracked or is about to fail. So these are all very important applications that are used commonly on our everyday life. However, there are several limitations related to these acoustic systems. The first limitation is that most of these materials and most of these systems rely on technology that is roughly 30 to 50 years old and is very mature. So it's very difficult to come up with new technology to improve the current devices. So the first application that we mentioned was the use of vibration absorbers for reducing, for example, noise or vibration in aerospace or mechanical application. So usually what industry does for these systems is to utilize rubber or polymer layers, foams or bulky systems to absorb or damp the vibrations that are undesired. One counterside of these, or one problem of these systems is that they are broadband and passive, which means we cannot target specific frequencies. So the absorption and the reduction of vibrations is actually across the board. So in some cases, they don't allow propagation of, for example, desired sounds. On the other hand, they also perform poorly. If you think about polymer layers or rubbers, they perform poorly when it comes to extreme environments like in space. The biomedical fields uses probes or transducers that generally have a fixed focal length. So as you've seen before, in the case of ultrasonic imaging, the resolution is very poor, and it's very difficult to, for example, acquire three-dimensional images. Now, this poor resolution not only reflects the fact that an image like this really does not quite give credit to the beauty of a baby, but wouldn't it be great to actually be able to see how a child would become once born? Now, I could do without colors, but nonetheless, I think we could definitely use some improvement on how ultrasonic images are obtained today. The last application is the one related to non-destructive evaluation of materials. Now, this one also utilizes transducers that are positioned in the systems and emit acoustic waves throughout the material and then pick up the signals back. Now, the problem in this case is that they rely on cumbersome and very expensive devices that are application-specific. So it's very difficult to actually utilize the same setup, for example, to test different parts of an airplane. What all these systems have in common is that they rely on dissipative, linear, and oscillatory signals. Now, that means that they are non-tunable. So once we have a system that's fixed and we cannot really easily change it, they rely on the propagation and the use of small amplitude waves, and they're often, as a consequence, ineffective. So that said, a solitary wave forming in a chain of particles is an acoustic wave, but has unique properties. So what we are doing is that in our lab, we design new materials and improved acoustic systems exploiting these and other properties deriving from the materials component. So let me underline and list for you a series of fundamental properties that solitary waves have in a chain of particles. The first one is the one that we mentioned at the beginning, that the spatial size of a solitary wave is finite, and it's always equal to 5 particle diameters. Now, 5 particle diameter is independent on the size of the particle. So this means that the system is completely scalable. So you can think of having new material systems composed of particles like the Newton Cradle toy that you see there, or scaling it down to the micro and nanoscales, for example, to achieve different frequencies and different acoustic responses. Another property that solitary waves have is that there is no characteristic speed of sound. So what does that mean? Is that in a chain of particles, there is no characteristic constant sound speed. So this is very unusual because it's counterintuitive, differently from, for example, what we know for linear materials. We know what the sound speed sound speed is in air, for example. We know what the sound speed is in a block of steel, but we really cannot say anything about the sound speed of a long Newton's Cradle toy. So one thing that's interesting in this case is that the propagation speed, or the solitary wave speed in these systems, is actually a function of the amplitude of the wave. So there's a nonlinear function. You see it by this proportionality equation, which actually means that large amplitude waves travel faster than waves that have smaller amplitudes. Now, this is also related to the fact that actually we can take a uniform system of beads and compress it. So imagine taking a long Newton's cradle toy and compress it or squeeze it with some force. Now, the wave speed in this case can increase. The solitary wave speed, or the wave speed traveling through these systems, can increase as a function of the force F0 that we statically apply to these chains. So this means that the system is tunable. Now, tunable means not only that we can change the speed of propagation at will, but changing the speed allows us to, for example, determine the frequency content that this acoustic, the acoustic wave that travel through these systems carry. So let me show you a graph demonstrating this phenomena. So what you see here is that on the x-axis, I'm plotting dynamic contact force, which means wave amplitude or solitary wave amplitude for a system of uncompressed particles. Now, what you see is that the dots represent experimental points, and the continuous lines represents numerical simulations obtained by computer calculations and theory perfectly overlapping. So what this demonstrates is that if I have a wave that has a varying amplitude or varying amplitude on the x-axis, you'd see that the wave speed actually corresponding to each amplitude is different at every point. Now, if we apply a static precompression, meaning if I take the same system and compress it with some static force F0, you'll see that actually all these points shift up, and I can tune now independently the wave speed as a function of the amount of precompression I'm applying by the shift of the blue curve with respect to the pink curve, and also as a function of the amplitude of the waves. So this gives me a lot of variability, a lot of control for the speed of propagation of these waves. So what is the fundamental key element for this to happen? So why is a chain of particles so special? So the key for this unique behavior is related to the particle's geometry. And the particle's geometry ultimately affects the particle contact, or the contact interaction of when two beads come and interact with each other. Like when I swing one of the beads on the Newton's cradle, that impacts sequentially the others. So what you see here is actually a computer simulation showing two particles coming in contact with each other. The first particle on top is going to move towards the bottom particle. And what you see here is only a section of the particle zoomed in close to the area of contact, because for symmetry purposes, we have reduced the size of the spheres to simplify and reduce the simulation time. So what you see is that the particles start from a point of contact, which ideally is infinitesimally small. And then once the two particles come close together, you see that the area of contact, which is this line over here, increases. So basically, we're going from one point of contact between the two spheres to a disk, which increases as the particles come together. Now, these fringes that you're seeing here actually are stress fringes, which means this is elastic deformation of the particle contact as the particles compress relative to each other. Once the particles come off and separate, you see that the fringes disappear, so there's no more elastic stress interaction, and in fact, the contact breaks apart. So we let the particle move away from each other. This is prescribing a contact interaction which is asymmetric. So in compression, we will have an elastic response, which is nonlinear due to the fact that the area changes nonlinearly with the application of load. And in tension, so when the particles move away from each other, we have no force or no information can be exchanged between these two particles. This is also why the spheres in a Newton's cradle toy can come apart. So we have said that the particle's geometry and the contact interaction affects dramatically the propagation of these waves. And one of the questions is, well, what happens if I actually change the particle's shape? So we ran some experiments and simulations to show what happens if we compare two identical chains in which we take the same number of particles, same material, and same striker velocity, and compare the variations in wave speed and variation in pulse shape in the two cases. In order to do this, we ran an experiment in the lab, and you'll see the setup over here. So let me explain how the system works. In this case, we constructed a more high-tech Newton's cradle, which is positioned vertically to ensure that the particles remain in contact with each other before we run the experiments. So the chain is composed by 40 steel particles, and then it's stopped at the bottom by a table to avoid, having separation between particles at the end. We use sensors embedded in some of the particles. In this case, these are instrumented particles with piezo materials, which is a material that reacts when a compressive wave passes through with sending an electrical signal to an oscilloscope, which is then picked up by a computer. And then we trigger by a mechanical drop, calibrated the impulses in the chains. Analogously, we have set up a chain of cylinders composed by 40 steel cylinders aligned together with the same height of the particles chain, and we have embedded selectively sensors in the same position as the sensors in the chain of spheres. And then we trigger with a similar particle drop wave propagating in these structures. So let's look at the experimental setup. The sensors, so these two schematic diagrams show the chain of cylinders, the 40 particles chain of cylinders, and the 40 particles chains of spheres. We have embedded sensors in particle 10 and 35. So the sensors are color-coded with the signal that's plotted in this diagram. The diagrams are showing force as a function of time. So you'll see that the first sensor, the sensor in particle 10, is going to pick up the first time response when the first impulse arrives here, and then eventually it reaches the red sensor, which is in particle 35. So by looking at when the signal arrives on these waves, we can actually calculate the speed of the propagating signal. In this case, so in the case of the stainless steel chains, you see that the delta difference between arrival at particle 10 and 35 is very small. Now, this means fast speed. Instead, in the case of chain of spheres, the delta time difference between the arrival at particle 10 and 35 is very large, which means slow speed. And you can see just by changing the particle shape, we can change dramatically the wave speed of propagation through the systems. In addition, and this is very important, you'll see that we can also tune or control the particles, the wave shape in the two systems. So in the case of spheres, like we mentioned before, the experiment shows the formation of these perfect solitary waves that is 5 particles long. While in the case of cylinders, you'll see that the wave shape is dramatically different, and it's actually representing, in this case, an oscillatory shock profile. Now, this is much less controllable and includes much more dispersive elements than the case. Dispersive meaning the properties of these waves tend to change as the signal travels through the system, while this one is extremely stable and compact. So that said, and after we have learned what the properties of, or the unique properties of a Newton's cradle or a longer Newton's cradle are, the question is, well, then how can we create new materials knowing this? The idea that we are leveraging is to utilizing particles as building blocks, a little bit like thinking of Lego blocks to form different structures. So one thing we've learned is that we have a way to tune the properties of the wave propagating in this system, so we can control acoustic waves in this new material by changing the shapes of the particles. At the same time, we can fix the shape of a particle, for example, taking spheres, and change the materials that are composing these particles to vary, for example, the signal speed. And finally, we have mentioned that it is possible to control the wave speed by applying a precompression to the system. So this brings us to the idea of constructing artificial crystals. Utilizing particles as building blocks, we can now construct artificial crystals by assembling particles in specific geometries. And the analogy here is to look at the fundamental structures of atomic crystals that everyone here is probably familiar with from classical fundamental chemistry classes. In this case, atoms, this is a diamond structure, by the way. Atoms are connected by bonds That can be, for example, ionic bonds or covalent bonds, depending on which kind of crystals I'm considering. And the bonds are what allow us to transport information between one atom and the other. So we can take the same idea and construct now macroscopic artificial crystals utilizing spheres as building blocks or as artificial atoms. Now, differently than in the case of atomic crystals, we can utilize elastic contact energy or elastic contact force interaction to determine how information travels through these crystals. And we can use, for example, different colors here represent different materials to create not only uniform systems, but also heterogeneous systems. So once we have designed these crystals for achieving specific properties and specific acoustic propagation and transmission properties, we can build 1, 2, and 3-dimensional systems to address specific needs of engineering applications. So what are the applications that we've been focusing on, and how have we, I guess, addressed some of the needs on the different fields of acoustic systems? So the first example I'm going to be describing on is the shock-absorbing composites. In this idea, we are trying to let's assume that I want to design a new material, a new composite to protect some delicate equipment underneath. So here is the fundamental problem. I have an impact coming from the top, and I want to protect my margarita glass on the other side. Now, margarita, because today is Cinco de Mayo, so I thought I could be in theme. So what would happen here is that there is a blast or a shock arriving from the top, impacting a material which I need to design, and trying to protect the margarita glass that's sitting on the other side. So one of the fundamental questions is, how can we design a crystal that would protect this system and avoid the forces and energy traveling from the blast and reaching the other side of the material? The idea we follow is to create, via numerical simulation, an assembly of particles that, by controlling their dancing motion and interactions, could protect and reduce the force amplitude transmitted through the crystal, and rather trap the energy in the core of the structures, or perhaps send even the energy sideways. So we can take a blast or an impact as the acoustic excitation coming in, and then redirect it in different domains. Now, you can see this effect more clearly on the diagram on the right. In this case, what I'm plotting here it's a 3-dimensional diagram in which the contact forces are on the vertical scale. So contact forces meaning we're going to record in every point of this dancing motion of the particles the force exchanged. And what we want to see is that the forces transmitted on this side, which is the side where the margarita glass is sitting, are reduced to a minimal point. So the red arrow in this case represents the direction of the impact or the blast transmitted through this crystal. So this green area is as if I take the crystal that you see on this side, tilt it downward, and then measure the forces on the y-axis. So what you see in this case is that this dancing motion of the particles in the crystal distribute the impact arriving on this side over a long and extended period of time between the particle, and the force amplitude that arrives at the side where the margarita glass is sitting is extremely reduced. So to understand better the analogy of this behavior, think of it as taking a big hammer hit on one side and breaking it into a series of separated taps that you can do, for example, with your finger. So the energy is conserved, and the sum of the energy of each individual tap, of course, sums up to the initial energy that we input in the system. But you see that the fact that they arrive so separately, and in most cases over a long and extended period of time, can protect the margarita glass very, very effectively. So for this project, we are working with the Army Research Office to develop new protecting systems for soldier and delicate equipment. Now, in Army speak, these are called energy dispersive composites. I can't tell you more, but you can use your imagination. We actually also hold a patent on the design of some specific protective systems. The second application that we've been focusing on it's analogous to the first one, and actually utilizes particles to design new materials for vibration absorption. Now, in this case, we have to imagine to strike or excite one-dimensional particles, a chain of particles, with not anymore with a single impact, but with continuous excitations. So here, what you should think about is longer Newton's cradle toy, which is composed now by two different sets of particles. The colors here represent different materials. So I can periodically distribute, for example, steel and aluminum in a sequential fashion. In addition, I'm going to apply a static precompression to this chain so that I can squeeze the particle to control the wave speed. So what you'll see, and this is the experimental equivalent of what you've seen in the schematic diagram, is that a system like this supports the formation of something called a band gap or an acoustic band gap. Again, a band gap is a region of frequencies in which no waves can travel or propagate, and actually the frequencies, the waves that are within the band gap are completely reflected backward. So what you see in this diagram here is an experimental measurement of the setup that you see up here, in which acoustic waves, in this case noise, white noise, is emitted on one side and measured on the other side. So we call that force transmission. So the force that is input, for example, in this side, which is where the actuator drives, and it's measured on the other side. And you'll see that the presence of this band gap that I was mentioning before causes the possibility of having band passes in which acoustic waves can travel at specific frequencies and then are completely absorbed on this side and can travel again on the other pass band and cannot travel in the upper stop band. So what does this mean? It means that we can create crystals or systems that can selectively absorb vibrations that are undesired, but that let other acoustic excitation travel through when desired. For example, we can use head protecting devices for soldiers in which we can, or ideally, design systems in which we absorb the sound of or blasts and sound of shots and let communication or voice communication pass through. The interesting thing of these granular chains is that by controlling the static precompression, we can move the edges of these pass and stop bands. So it is possible to control in situ which frequencies are allowed to propagate and which frequencies are being absorbed. So for this specific thing, it's easier to perhaps understand the behavior of these systems by looking at this diagram. This shows an experimentally obtained measurement in which the blue curves represent a single excitation, so a vibration that is inputted in the chain of particles at a frequency within the pass band. So this is the allowed band propagation, while the red curve is a frequency excited within the band gap, which means the not allowed, the no pass band. So you'll see that in the case of the frequency excited in the band gap, nothing really travels through, and there's only noise within the zero, around the zero amplitude. So for this material, we are working closely with the Northrop Grumman United Technology Research Center and also JPL to develop specific applications targeting selected ranges of frequencies, for example, for absorbing annoying vibration in Earth observing satellites, as well as for absorbing sound or unwanted noise in helicopters, and finally to mitigate launch vibrations in payloads with JPL. So the next application I'm going to be describing is the use of nonlinear acoustic waves, or in this specific case, solitary waves, to test non-destructively material systems. So the idea here is that we are envisioning the use of solitary waves and the use of granular materials supporting solitary waves to evaluate the integrity of materials. So this schematic diagram shows the idea behind our work. Now, we can use, for example, and position a chain of particles, like a longer Newton's cradle toy, next to a given system or a given engineering material. Now, these particles, if we strike the chain from the top, we know they're going to form a solitary wave that will come to interact with the boundary and eventually travel through the adjacent material. the sound wave that's going to be inputted in this material will interact with the presence, if any, with the presence of flaws and defects and be reflected backward. By analyzing how the reflected pulse travels through the chain, we're able to predict whether cracks, for example, fatigue, or defects in the materials are present. So what's the advantage of this setup is that the advantage of using solitary waves and granular systems is that they provide a much larger range of tunability and control of the frequency, for example, inputted in these systems. They require no function generators, for example, in the case of transducers used in common technology, and they're extremely scalable, and of course, they are very low cost. So this one perhaps is the technology closer to commercialization that we are developing in our lab. In fact, it can address different problems in different engineering systems, starting from aeronautical and aerospace, for example, by looking at delamination between composite systems, or looking, for example, at civil infrastructures in which, for example, railway switches can be monitored to avoid train disasters. Or we can use them, for example, in biomedical application to test the viability of implants. In this case, you can see here a hip implant to see if the implant and the bone regrowth are consistent with what expected by the healing patients. In this case, we can also test, for example, new implants developed by the biomedical industry. Now, this work has been supported by NSF so far, but also a couple of years ago has spun off into a startup company. Now, a startup company got a lot of attention in Europe. In fact, won the INSEAD business venture competition. But since then, we got really busy in the lab. And in fact, we're currently looking for a CEO. So for the board executives in the room, please come see me after the talk. Anyway, so how does this technology work? In the past, we have developed designed a new actuator system that runs on regular batteries, which can trigger and control the formation and propagation of solitary waves. So let me show you in this cartoon. This is the device, by the way, pictured in the lab. And this is the cartoon that explains how the system works. So what you see here is that there is a motor, battery-controlled motor with a lever system that can lift up the particle, load up a spring that's going to be released once the lever moves backward, and lets the particle drop. Once the particle drops, a solitary wave is formed in the system, travels through the chain, and eventually interacts with the boundary and with the presence of defects, if any, in the adjacent structure. Once the wave reaches the defects, it's going to split into a portion that travels through the material and a portion that travels backward. The one that travels backward is going to reach the sensors that are embedded in the particles, and the connection of the sensor through a computer, like you've seen before in the experimental setup I've shown earlier, allows to determine if cracks are present or defects are present in the structures being investigated. Now, the final application that we've been focusing on, and this is most recent development, is the design of new acoustic lenses based on nonlinear granular systems. The study of these systems has allowed us to discover the generation and propagation of something that we call the sound bullet. Now, sound bullets are highly compact acoustic pulses that form in solid or fluid media, and they derive by the superposition of several solitary waves traveling in parallel chains of particles. So imagine assembling several array or several Newton's cradle toy, while each one next to each other, independent from each other, and deriving the solitary waves traveling through them, eventually being focused in one specific spot. Now, we have recently published these results in the proceeding of the National Academy of Science, and we thought to be the first one to having thought about sound bullets. But doing some careful searches, I've seen that actually already in the 60s, the Mattel came really close to it.
You must not fail 0M. This mission is critical. unusual weapon. It is specially designed for counter-espionage, for Agent 0M. It's called the 0M Sonic Blaster. This is why. It fires a massive blast of compressed air, and this tremendous roar is the actual sound. For training purposes, this special delayed action target comes with it. Get Mattel's powerful 0M Sonic Blaster wherever toys are sold. Remember the password, 0M.
Now, our sound bullets derive from a much more high-tech device. It's not composed by a bundle of compressed air, but rather by a superposition of nonlinear solitary waves. But let's look at how we generate these sound bullets in the lab. So this is a picture taken in our lab of the acoustic lens that has been tested and studied. What you're seeing here is an array of 21 chains of particles. These are all stainless steel particles. And by the way, they're particles that can be found commercially as ball bearings. And they're assembled, so there are 21 chains parallel to each other and independent from each other. And they're composed by 21 particles each. So let's review what I've said so far about the properties of solitary waves traveling in chains of spheres. We say that we can control the wave speed by controlling two things. We can control the amplitude of the waves, and we can control the static precompression, or how much we squeeze these chains independently from each other. So the results of that is shown in these numerical simulations obtained by computer calculations of chains compressed differentially between each other. So these are the 21 chains. So this part here represents the lens. And you'll see that the outer chains are more compressed, while the central chains are less compressed. The compression and the amount of stress or the amplitude of the acoustic waves is actually depicted in this diagram by colors. And you'll see that red colors means high compressive stress, while blue color represents high tensile stresses. The green color means that the system is at rest. So you'll see here that we start from a position of high compression on the outer chains. So the outer chains are more squished, which means that the waves are going to travel faster here and slower here. So what you see in this case is that if we play the movie, the solitary waves, and let me stop it. So the solitary waves travel faster here, and they're going to be emitted in this green block on this side, which represents a space filled with air. So once the solitary waves arrive to the boundary, they're going to be transmitted in air and eventually coalesce to one specific spot. And let me play this again. So the solitary waves arrive on the edges, travel through the system, and eventually coalesce in a spot, or a hot spot, which is the focal spot or the focal distance of the lens, and remain extremely compact. So you'll see that the sound bullet in this case is formed by two areas. One, which is this red area, which is a extremely high pressure compressive pulse, followed and trailed by a high amplitude tensile pulse. But all in all, the bullet is really compact. So it is followed by very low amplitude trailing pulses. So this is extremely unique because no other acoustic device can produce such pulse. In fact, in principle, these sound bullets can achieve arbitrarily large amplitudes and can be tailored to be positioned anywhere in the space adjacent to the lens. So how do we control that? We can move the sound bullet, for example, in different position in this area by changing the static precompression that's applied on each chain. So you can foresee, for example, that by instead of compressing more the outer chains and leaving the central chains less compressed, we can distribute the precompression in such a way that the bullet is moved in different locations. This slide represents a cartoon for how one could extrapolate the design of our two-dimensional lens that you've seen before in the lab to a three-dimensional system. So what you see here, the blue portion represents the lens, and the white area adjacent to it would be air. And what you see in this case, this flower-looking structure is a profile or a snapshot of profiles of the sound bullet forming at the hot spot, trailed by these branches over here, which are pressure profiles with extremely much lower pressure than the one in the middle. So to understand this better, let's look at the movie that represents the formation of a sound bullet in 3D. So what this movie shows is that this area over here represents the edge of the acoustic lens. So over here there will be several chains of particles compressed differentially between each other. And these areas over here are pressure profiles that are emitted from the arrival of the solitary waves at each point in the lens. So if I play the movie, you'd see, by the way, we're looking only at an image cutout, so you see basically only half of the portion of the formation of the solitary waves to allow to see more clearly the formation of the waves without shadows. So you'd see that the waves are emitted and eventually coalesce at this focal point, which is where the sound bullet is forming. Eventually, the sound bullet travels for a finite distance and dissipates away. We can control how far the distance, the bullet can travel, and where in a three-dimensional space the bullet is forming. You can imagine how this flexibility to obtain large amplitude constant pulses could improve the resolution, for example, of biomedical devices. In the top case, we're showing a cartoon in which we show the use of sound bullets for targeting specific areas or specific cells in the human body. In this case, the high energy concentrated in a sound bullet could be used, for example, in hyperthermia treatment for increasing the temperature of localized cells in the human body and selectively kill the undesired cells. So in this case, we would, for example, target tumor cells. Analogously, such compact pulses could improve the resolution of ultrasonic imaging. Now, once again, for the board executives in the room, you might all agree that the use of sound bullets for ultrasonic imaging might not be the best way to commercialize, and we would probably have to find out a better way to address these systems. But nonetheless, the large amplitude and the compact shape of these pulses could significantly improve the resolution of acoustic imaging. So with that, I'm coming to a conclusion of my talk, and I'm going to be summarizing what I've said so far and talking about the fundamental applications of nonlinear acoustic crystals, starting from the understanding of the dancing motion of a Newton's cradle toy and the fundamental physics misconception on the conservation of momentum from particle to particle. We've come to design 1, 2, and 3-dimensional crystals composed by longer version or larger assemblies of particles of different shapes and with in different conditions. And we have addressed problems like absorption of noise and vibration in aeronautical and aerospace application, as well as utilizing these waves for non-destructive evaluation in material systems. And finally, addressing problems, for example, in the biomedical industry for acoustic imaging, as well as targeting tumors, for example, in acoustic surgery. So I'm going to wrap up my talk by thanking the entire all the group members that have contributed to this work. And I'm going to be focusing in particular on the 4 of them, Alessandro, JK, Nick, and Dev, which have contributed significantly to the slides that you've seen in this presentation by coming up with movies, simulations, and even experiments in the lab. And last but not least, I should also thank all the undergraduate students, SURF students, and visiting students that have been rotating in the labs in the past 4 years or so, which have contributed significantly also to the results you've seen so far. And finally, also thanking the funding agency that have made all this possible, in particular the Army and the National Science Foundation that have contributed to most of the work you've seen in this presentation. And with that, I'm going to wrap it up, and thank you all for your attention.
This program is brought to you by Caltech. Visit us at caltech.edu.